This chapter on systems of many particles is a pretty in-depth one. And so this is probably going to end up being several videos that you can watch in sequence. Um, System of many particles essentially is the physics term for thermodynamics. And so we're going to be going through a lot of thermo that you will see in physics or in chemistry 371 or some other chemistry classes. But we're going to be looking starting from the physics standpoint and working our way there. So let's talk about some of the things that will be there. Um, so we're going to look at how you model large number of particles. You know, you've already done a lot of this in chemistry classes. You just didn't know that's what you're doing. We're going to lay the groundwork for later chapters by looking at the Boltzmann factor, the equation of energy, chemical potential, Gibbs free energy. This is all working towards the thermodynamics in the context of the cell, which will be applied in later chapters. And so this is sort of where this chapter is headed. It's laying the groundwork for chapters 4, 5, 6, 7, 8. Those you kind of need the concepts here um, in order to progress through those chapters. Um, all right, gas molecules in a box. Molecules aren't individuals. And so when you start looking at how many different states we have here, you know, we say, oh, we've got a molecule over here, a molecule over there, and or we could have two molecules here in the right. We could have one in here and one in there, but we don't know which one it is. So that actually happens twice, right? And then we can have two over here. And um, so the probabilities depend on the fact, in part because these are not these particles are indistinguishable. These molecules are indistinguishable. It's not like we've named one Mary and one Larry and we can keep track of which is which. No, they're just oxygen or they're just whatever they are. Um, so the probability of finding a particle, you know, in a particular volume is the volume the particle takes up over the total volume. So if you have n particles, you start looking at, oh, here we go. We got this. This is a binomial um, theorem or binomial distribution. So in factorial, you probably know what a factorial is. If not, ask in the discussion thread. So the total n is the total number of particles. Um, Small n is the number we're looking for in terms of how many are in this particular state. P is the probability of being in a particular state. And so this all works out is a nice, if you remember, it's sort of a nice Gaussian-like curve, but not quite a Gaussian. If we look at the total energy of a system, it's the sum of the energy of all of its parts. Right. So here we've got a bunch of particles in different energy levels. The total energy is there are two in U23, there are one in U25, one in U26, three in U28. So heat flowing into a system, these are just getting terms down. Heat flowing into a system we label Q. Work done by the system we label W. These pictures down here are different ways of picturing systems that we're going to work with, so we can draw a picture and not have to say as many words. The double wall of this box means it is thermally isolated, and that's going to be it's thermally isolated from its surroundings. Here, there's a thermal isolation, but work can be done because there's this piston that can be introduced work into the system. Here, it's not thermally isolated. All right, no isolation thermally here at all. That's a single border. Other things you'll get the first law of dynamics. Change in energy of a system is heat flowing into it minus work done by the system. So heat flowing in minus work done by the system. You're going to have some problems that involve dietary calories. A dietary calorie is 1,000 calories, and 1 calorie is 4.184 joules. So one dietary calorie is 4,184 joules. It's important that you pay attention to that capital letter right there. Why do we have a dietary calorie be 1,000 calories? Because we don't want to scare people and say there are 250,000 calories in this Snickers bar, um, or a million joules of energy in this Snickers bar. We don't want to do that. Macro states are the big variables that define the collection as whole. Pressure, volume. These are external things that you can measure that have nothing to do with individual particles. So macrostates are properties of the collection as a whole. And we say if two systems have the same macrostates, they're identical. And now microstates have to do with the particles themselves. And so the number of systems in a particular microstate divided by the total number of systems in an ensemble is the probability of being in that microstate. And so a microstate here would be all the particles in one of these boxes is all the way on the left, right? And so, the probability of finding that, well, is going to be proportional to the number that are like that, which in this case I'm proposing 1, divided by the total number of boxes, which is 12. Basic postulates that we're going to be working with. Equilibrium is one of the key concepts that we're going to work and go back to again and again and again and again, because very often we cannot successfully describe the system in its dynamic states, but we can describe it pretty well once it's in equilibrium. Um, so if it's not in equilibrium, systems tend to go to equilibrium. That's the most random, most probable state. Right? So at equilibrium, you have the most microstates. So take the total number of microstates to be, use the symbol omega, right? So you've got all kinds of microstates a system could be in. In some number of them, omega x, they have this one value of the property x. That means the probability that you have that x, p sub x, is the total number of microstates with omega x divided by the total number of microstates. It kind of makes sense. All right, we're going to stop here with the microstates, and we're going to pick up again on the next segment.